Valence bond theory. Right, so now we turn our attention to the more advanced theories of covalent bonding. Exactly how do two atoms share their electrons to make a more stable, lower energy sort of a arrangement that we call a covalent bond. We have to think about the distance between the two nuclei. How far apart do they need to be to share, or how close do they need to be? What about the energy of the whole system? If it's more stable, it should have a lower energy. We have to talk about the geometry. How do they arrange themselves in these sharing configurations so that we can get tetrahedrals and octahedrals and that kind of a thing? All right, so valence bond theory looks at the energy and the distance of a covalent bond. And to keep it simple, we start off with the idea of just two hydrogen atoms. They're going to come together and they're going to make that bond. What does that distance and what does that energy look like? And here, this potential energy curve, it's actually called a Lennard-Jones potential curve. As you can see, I've got on the y-axis energy and on the x-axis distance. Distance in this case in picometers, so the distance between the two nuclei. And we talked briefly about this in the previous chapter as well. The idea that if they're far apart, we have no interaction at all. And with no interaction, we're going to call that potential energy zero, which makes sense. And as we get close together, it starts to slide down because we're stabilizing. What happens is that as they come together, the electrons start sensing the other nuclei. That's an attractive force, and the energy actually drops. And as we come closer, though, those orbitals that those outer valence electrons are in begin to overlap. Excuse me, and it's that overlap of the orbitals that creates the covalent bond. As I'm sliding down here, I'm getting more and more stable, lower and lower energy, getting closer and closer together. Now, if you think about it, though, if I start getting too close, I start crowding those electrons, trying to shove them into a tighter space. On larger atoms, I would actually start getting repulsion from the inner core and the other electrons as well. And not only that, but the nuclei. The nuclei are getting closer and closer, and they're positively charged, and so at some point they're going to start repelling. And so, yeah, I've got stabilizing forces, but I've got repulsive forces as well. And I'm trying to balance those out essentially. As I'm going down here, the stabilizing forces are winning, if you will. At this point, they exactly finally balance each other out, and I come to a minimum. If I try to go closer, I go shooting up very quickly because the repulsive forces dominate the attractive ones. And so I've got this optimal distance right there, in this case 74 picometers for an HH bond. That'll be what I call the size or the distance of an HH covalent bond. And the drop from 0 all the way down here, how far down did it go? In this case, it went down 7.24 negative 19 joules. But that drop going all the way down is the strength of the bond. Another way to think about that is that's how much energy I'd have to put into an HH bond to pull the atoms apart and release them as single atoms. Alright, so the Lennard-Jones type potential talks and shows correctly the energy associated with a covalent bond like that. The table in the textbook shows some of these different lengths and some of these energies for different atoms in different bonds. And so, for example, we just looked at that HH bond. The length was 74 picometers. The energy 436. They've changed the units here to kilojoules per mole instead of just joules of a single HH bond. So here we got a mole of them, and they're given in kilojoules, and that's usually the unit that is easier to compare. If you look at the different ones, what if I did an H to a C, an H to an N, an H to an O? They all have their optimal distances. Well, I think it makes sense because the different atoms are different sizes, and so they're going to have unique distances. And the energies, how much they actually drop, again, they're in the same ballpark, but they are fairly unique. Couple trends to notice here. Look at the carbon-carbon ones. If I do a single bond versus a double bond versus a triple bond, the lengths decrease. That is to say, the longest one is a single bond. As I put 2 bonds in there, that tightens it up and it actually gets shorter. 3 bonds tightens it up even more and it gets shorter yet. I think it makes sense that the bond energies also increase from 347 up to 839. Yeah, the more bonds I have, the more energy it would take to actually break those bonds and separate those atoms. Right, and so that trend generally holds true. Here's a CO, C double bond O, C triple bond O, and those same trends hold true for that as well. Also look at something like this, the chlorine, the bromine, the iodine. This is going down. If you look at a periodic table, this is going down the halogens here, chlorine, bromine, iodine, and we know we're getting larger and larger atoms as we go down. And so as I look at those, look at the distances, 127, 141, 160, just simply reflecting the size of those halogen atoms. So I think that makes sense. The energies associated with that, 431, 366, 298. As I go to larger and larger atoms, the bond energy is actually smaller. It doesn't stabilize as much. And that's because they can't get as close to each other. So you don't get those attractive stabilizing forces that you would get in a smaller one. Right? And so small ones here, like an FF, 159, 142, or Cl, longer because it's bigger atom, and 249 for the stabilization energy. All right. Sigma versus pi bonds. Now in this case, we are talking about the type of overlap that you can get between the orbitals of the two atoms. If we get them to overlap, we can put them at that optimal distance, we get a bond, right? And they're going to share those electrons in the overlap region. There's two different ways I could overlap atomic orbitals. I could do it with just a single region of overlap, or I could do it with two regions of overlap. Now keep in mind, I've got one orbital, one electron here, another one, and it doesn't matter how many regions I overlap those, maybe 3, something like that, or 2, or just one region to overlap. It's still just a single bond that I'm actually creating in each case. And so in this case here, look at, here's two s orbitals. I've got one atom on the left, one atom on the right. These s orbitals, as they come together, remember s orbitals are spherical. As they come together, they start to overlap in this single region, this darker area in between. Here I'm doing an s with a p. But again, the overlap is just a single region, or maybe two p's, a single region of overlap. All of those would be called sigma bonds. A pi bond is the second way that I could overlap these orbitals. With a pi bond, I actually have two regions of overlap. Right? And so here's the example, is 2p orbitals. As I bring those together, of course, I've got these nodes right through the middle where there's no electron density at all. But then I've got one orbital here on the right, one orbital on the left, and when they come close together, they actually overlap in two regions, the top and the bottom. But again, that is a one additional bond, this one single bond here. That doesn't count as two. It's still an orbital and an orbital overlapping, so there is a bond, just like a sigma bond here is a bond. Alright, now to form the traditional single, double, triple bonds, I'm going to be overlapping these atomic orbitals, right, in the different ways that both sigma and pi's can do so. A single bond is always composed of a sigma type overlap. So a sigma, or one region, right? A sigma bond. If I have a double bond between two atoms, then I'm going to need two types of overlaps. And it's always going to turn out to be a sigma and a pi. So I'm going to have one that overlaps in one region, and the second bond that gets formed of the double bond, right? The second bond actually overlaps in two regions. For a triple, it's a sigma, a pi, and a second pi. Always going to be true. So you can definitely take this kind of a thing, box it, if you will. This is very, very important to remember, and it's always going to be that way. There's no variations ever in that. Alright, so quick little example here, HCl. Well, you've got a single bond there, so hey, there's one sigma, and that's it. Oxygen molecule, you got a double bond, so in that molecule I've got a sigma and a pi. Well, because that's what makes the double bond up. A triple bond here, sigma and a pi and a pi. No matter what the covalent bonding structure looks like, you can always look and see what kind of bonds you have, what kind of overlaps. Example 8.1 does that with a larger, more complicated molecule. All right. I've got actually 4 carbons here. I've got double bonds, I've got a single bond, I've got H's that are single bond. And the question is, well, how many sigma and how many pi bonds are in that molecule? Pretty simple to answer that. I just kind of count them up here. If I look at all the sigmas, all the singles, which mean just a sigma, I've got 1, 2, 3, 4, 5, 6, 7. So there are 7 single bonds, and that corresponds then to 7 sigmas. Then I've got 2 double bonds. With those 2 double bonds, I'll have 2 sigmas and I'll have 2 pi's. And that's all the type of bonding that I have. That makes a grand total of 9 sigmas and 2 pi's. Those are the type of bonding then that would be in that larger molecule.